Guys, I'm going to answer the questions on 27.1 for you now, energy and mass. And you're given two values. You're given the rest mass of an electron. It's called rest mass because electrons and protons and neutrons are very, very small. If you make them move very, very fast, near close to the speed of light, they actually gain mass. This is due to Einstein's relativity, general relativity theory. So rest mass would tell you its actual mass if it was staying still. Okay, we also know G is 9.81. So question 1 says calculate the mass increase of a 10 kilogram object raised through a height of 2 meters. So the change in energy there is going to be GPE, which is equal to mgh. So 10 times 9.81 times 2, which gives you an answer of 196.2 joules. Then you're going to use the change in mass is equal to E over c squared. And c is 3 times 10 to the 8 squared. So that equals 2.18 times 10 to the minus 15 kilograms. For B, we've got the electron. And it's being accelerated through a voltage of part 1, 5,000 volts. So the gain in energy is electrical energy, so E equals QV. Q is the charge of an electron, which is 1.6 times 10 to the minus 19 times 5,000. That gives us an electrical energy of 8 times 10 to the minus 13 joules. The change in mass, according to Einstein's principle, would be 8 times 10 to the 13 over 3 times 10 to the 8 squared, which gives us a value of 8.9 times 10 to the minus 33 kilograms. And then for part 2, we've got 5 megavolts. Okay, so the equation's the same, but you've got megavolts there. So the answer to this is obviously going to be 8 times 10. Oh, sorry, that's minus 16, that one. I was reading the wrong answer. This one's minus 13. You should still get that answer there. Joules, and then change in mass equals E over c squared, which is 8.9 times 10 to the minus 30 kilograms. Sorry about that. I tend to do the questions first and then I just write down my answers, but I read the wrong bit on that because the equations are similar. So that's minus 16. You should still get this answer here, and then this one's the minus 13 one. Okay, sorry if you got stuck on that bit. Right, part 2. You have a bismuth 212 emitting alpha particles, and it decays to form 208 thallium. It says write down an equation for this process. So I've written that, and then 83 minus 81 is 2. 212 minus 208 is 4, so it emits 1 alpha. Okay, and then it wants the energy released. So you've got the values there for the different nuclei. So you're going to do the change in mass is equal to 211,94562 minus 207.93746 minus 4.00150. That gives you a change in mass of 6.66 times 10 to the minus 3 U. 1 U is 931.3 mega electron volts. So the energy is going to be 6.66 times 10 to the minus 3 times 931.3 mega electron volts, which gives you an answer of 6.20 mega electron volts. That's for B, part A. For part 2, it's a written thing. It's explaining that calculation why the thallium nucleus in the above decay gains a small proportion of the energy released. It's to do with conservation of momentum. So this is one nucleus before, so it has 0 momentum because it's not moving. But then you have 2 after, so one has to move one way and one has to move the other way. So the momentum of each one cancels each other out to make 0 for the first one. And so some of that energy is used for kinetic energy to move them apart. Question 3. You've got a strontium isotope emitting beta particles. And it decays to form a stable isotope of deuterium. Write a nuclear equation to represent this. So 1990, 0, so that's right. And then 38 plus 1 is 39, so that's right. So 39 minus 1 makes 38. So there's only one beta. Write down and then it wants you to calculate the energy. So you're just going to do exactly the same as you did before. The change in mass will be the mass of this, which is 89.88640, minus the mass of this, which is 89.88525, minus the mass of the beta, which is 0.00055. Gives you a change in mass of 6 times 10 to the minus 4 U. We know 1 U is 931.3, so you're going to do 6 times 10 to the minus 4 times 931.3. This gives you an answer of 0.56 mega electron volts. And then in B, explain without calculation why the kinetic energy of the beta particles released decays up to varies from 0 up to a maximum. It's because it depends where in the nucleus the neutron that turned into a proton and electron was. I mean, if it was at the edge, then right on the very, very edge, the beta could just escape, so it would have the maximum amount of energy. But if it was on the inside, it would require some energy of its kinetic energy to actually escape. So that's why they're up to a maximum. And then some of them wouldn't actually escape at all. They wouldn't have enough energy to escape, so that would be the 0 value. Right, question 4. We've got copper 6429, and it decays through electron capture to form a stable isotope of nickel. Write down an equation to represent this process, that's what I've done, and then calculate the energy. So in this case it's slightly different to this one. So in this one you've got one nucleus turning into 2, but in this one you've got 2 things turning into 1. So you need to add these 2 together first. So you're going to do the change in mass is equal to 63.91381 plus 0.00055 minus 63.91256 gives you a change in mass of 1.8 times 10 to the minus 3 U. Your energy is therefore 1.8 times 10 to the minus 3 times 931.3, which is equal to 67634, equals 1.7 mega electron volts. And then it says state the name of the particle that takes away the energy released. by the electron in neutron capture. That would be a neutrino. Okay?